on the goniometer, on one side there will be a, maybe I'll be going back here. Let me explain this part, then I'll go back. So here is the X-ray tube, and the another one is detector. So from X-ray tube, and this one is the sample. So here you are able to see the circle. This circle is what we call goniometer circle. So this goniometer circle will be different actually. In different machine, its goniometer circle will be different. So you have a tabletop model and you have a full version models also. And in these tabletop model or full version model, what is difference is this diameter of this goniometer. So if you are using a smaller diameter, accordingly, you need to compromise with the resolving power of your X-ray. And if you are using larger diameter, maybe latest model or the advanced models, you can see that the goniometer diameter will be relatively larger, so that you will be able to resolve and get a better information from X-ray diffraction studies. So you can see the detector will be moving around a circle. Actually, this is what we are calling goniometer. uh, Detector is moving on this goniometer circle actually. So once it is moving on this, whenever it encounters with the diffraction, it's going to record it. So we are going to get it as a X-ray pattern. So it's a this information is plotted between the 2 theta and intensity will be plotted. And there are different ways we will be doing it. So we can use a Lave method where single crystal will be studied. So in this case, we are going to vary the lambda and theta will be fixed. And in case of a powder diffraction, in most cases, we will be using a powder diffraction. And powder diffraction, we can use a polycrystalline material, or in this case, where lambda will be fixed and theta will be the variable. And we can also use rotating crystals, where in this case also single crystal you can use, where lambda is fixed and theta is a variable. So of course the methods are for various purposes. We'll be talking about what for different methods are being used. And if you see the X-ray diffraction pattern, here is the typical X-ray diffraction pattern one can see. So the diffraction pattern, you can see K alpha 1 and K alpha 2 lines. So in addition to K alpha 1 and K alpha 2, we will have others also. So you can see K beta line is also there, tungsten is also there. So the additional peaks, maybe tungsten is from your X-ray source or X-ray tube, where maybe it was used as one of the target material, or somewhere tungsten may be used, or any other element is used. So we may be getting the X-ray peaks from those elements as well as K beta. So effectively, these information must be eliminated so that we get a right information. When we analyze this pattern, we'll be getting the right information. And unless we eliminate these peaks, we will not be able to provide the right information. But this is what the costly part is. Of course, there are filters are available. By using filters, we can remove these K beta information, we can remove it. But removing K alpha 1 and K alpha 2 is really challenging for us. So this one we can use a filters and remove it. Whereas this part is really challenging for us. So that's where we are going to use something called monochromatous. So we can use sometime monochromatous. So here you can see this is the sample position. Here from this point, X-ray sources emitted. From this point, F point, it is emitted. And receiving side, before it reaches the detector, you can use a monochromator. So what is this monochromator is used for? It is going to clean unwanted information. It can absorb it, so that we get a clean information from here. So any radiation, sometime the extensive radiation will affect the detector. So it will be also absorbed by these monochromators. And monochromators also help us to control the beam size. So here is an information. You can use some crystals. So before it goes into your sample, sometime we pass through this monochromators. So through by passing through this monochromatous, you can control the wavelength still more. The wavelength will be k alpha 1, k beta can be eliminated, and it's not sufficient to separate k alpha 1 and k alpha 2. Of course, separating k alpha 1 and k alpha 2 is very costly, very costly. So if you are using something like k alpha 1, k alpha 2 also experimentally removed, so those machines are really costly. And these monochromatous, usually we use a single crystals of silicon, germanium, lithium chloride, graphite, and so on. And sometimes we use a curved shape. I'll be talking about why we are using this curved shape of a monochromatous, so that the focal point will be very clear. If you are using a flat monochromatous, sometimes it won't get focused on a single point, so it's going to get focused on a multiple point. So to make it to focus on a single point, we can have a design something like curved design and all, we can have it. And as we have discussed, so we can use filters, and these filters will remove the unwanted wavelengths, which is k beta and tungsten lines, which can remove it. So this material has an absorbance edge will be there, and usually it is the element just below the target material. If you are using a copper, nickel will be used. Nickel is just below in the periodic table. It is just below copper. So the element lying in the periodic table just below the target material is used as a filter material. And of course, how much effectively it has to filter, it is decided based on the mathematical calculations. So here are some typical filters we are using for silver. For silver, we are using palladium. Molybdenum, we are using zirconium. Copper, we are using nickel, and so on. So there are few commercial filters are available, and of course there are some clients from the standard companies like Bruker and all. So you can see these two information. The first information, you can see the black information where we have the K beta information. So this K beta is eliminated by filter. Nickel is used as a filter. So you can see the intensity is reduced, and also still there is residual K beta peak is there still in the material. Whereas there are some standard filters are there which are patented by certain companies, where you can see the K beta line is completely eliminated. So depending upon what kind of technology they are using, accordingly the cost of the equipment is also involved. So filters are very important, and sometime when you are getting the X-ray pattern, and it's especially those who are working with steel and copper target you are using, and steel you are analyzing. In these cases you are going to get a background noise, very high background noise you will be getting. So your signal will not be very clear at all, your intensity is weak, and the noise is very high. So basically this is due to fluorescence actually. So if you have some material which where the secondary x-rays will be easily emitted, so when you expose this material to x-rays, so x-rays will be secondary x-rays will be emitted from them, so they cause fluorescence, so they are going to rise the background continuum spectrum, it is going to increase. So thereby your signal to background will not be very clear, so we are going to have a disturbance in the analysis. So here is an information how here is another a detector. So usually they correct it with the best kind of a detector. So again, it depends upon the detector, what kind of detector you are going to use. So usually in earlier days we used to have a one dimensional detector. Now in the market we have a two dimensional detector, multiple kind of detectors are available. So in a one-dimensional detector, you can see the signal. Hematite sample was analyzed, and you can see the signal. And background noise, you can see the intensity is very high. So the signal to background information is not very clear. And in case of if you are using a Bruker detector, where line eye detector you are using it, so in this case you can see very clear information between the background and the signal is very clear. So thereby you get better filtering effect by using a best detector. So what kind of equipment you are going to use, so that's going to affect your uh, the the signal clarity it is going to affect. Another thing is we are in X-ray tubes. We'll be using a shutter actually. So this is used for safety purpose. Whenever we are going to work with the X-ray, so please be careful when working with X-ray, because X-rays earlier days people were not knowing about X-rays, so they were just playing with X-ray torches. So they used to see their hands etc. using bones etc. using X-ray torches, and later it was realized that it's going to give cancer and other problems. So that's where very high safety is required. Of course, we have in India also we have the atomic commission, where if you are importing these kind of components, especially you have to take a permission from these bodies, you have to take a permission, because hazardous things you are handling it. So anyhow, when we are designing this X-ray, so you can see in the equipment also there will be a red light. I'll be showing in the demonstration. So this indicate whether your X-ray window is opened or closed. So if it is open, the red light is going to give you information X-ray is continuously coming out. So in that time, you should not expose, or you should not open the doors or try to open the door. Of course, recent days people have made a lot of technology where you cannot open unless the shutters are closed. So we carefully design how much X-ray will be absorbed by these windows, etc. So these are all designed based on the calculations, absorption calculation. We can do that. And of course, in X-rays, we have different types of scans. We can go for normally it is of theta to theta scan. So when from your X-ray source, the X-ray is falling on the specimen, and it's not these. The angle is not between your sample surface and the X-ray tube. It's about the planes, in what planes are exposed to X-rays. So theta to theta scans and theta theta scan. Shortly, I'll be talking about theta to theta scan and theta theta scan. And we have omega scan, we have kappa scan, and multi-axis goniometer, etc. So here is a view for us to visualize how the rotations are possible. So X-ray beam is falling, and here is this tip is a place where you can place your sample. So you can have a regular rotation is there for collecting the information, theta to theta information can be collected. But in addition to that, you have the provision to rotate it in various other angles. So you can rotate about the pi angle, you can rotate about alpha angle, you can rotate about the kappa angle, you can rotate about omega angle. So according to your requirement, you have to rotate in various directions. So this again, especially those who are working with residual stress analysis and all, they have to use this kind of a different rotational possibility. They have to use it. So to have a idea that how these rotations are going to help us. So here is what you can see. There is various rotational possibilities. You can see that in this video, and you can see this the incident beam is falling on this object, and we are going to get a polarized or a pole figure we are going to generate to create a pole figure, that is orientation of crystals or orientation of a film on a substrate material. So we have this kind of a scan. We call this pi scan, and chi scan is fixed over there. So you can see how the rotations are possible, and the chi is again fixed in different position. So you can place it in different position, chi and psi. Both you can place it in different position, and you can have different data you can collect it. By this way, you can get the information about the crystal orientation. So this is about the pole figure arrangement. So the experimental arrangement will be something like this. So in addition to this, if we talk about the regular theta to theta configuration, so here is the regular theta to theta configuration. So you can see the incident beam is falling on your specimen. So here is your specimen, and this is the detector. Detector is moving on a goniometer circle actually. So when it is moving on the circle, so it's going to collect the information and it's going to plot it as a intensity, 2 theta intensity plot. You will be getting it. And finally, we'll be getting a data something like this, where each peak correspond to different planes actually. So it's going to be reflected from different planes. If you physically look into that, of course, pole figure through EBST mapping, if you do that, each crystal is oriented differently. They have different planes. Different planes are oriented. So it's also possible that in some cases, what we will do, we are going to move the detector, and after moving the detector to a particular location, we will fix this angle between incident beam, that is source, and the detector. And both of them we will continue, sample will be fixed, both incident beam and detector both simultaneously we will be moving it. So which is called uh, theta theta scan we will be doing it. And this especially grazing incidence events, I'll be talking about what is this grazing incidence. So where you need to get information about the thin films and all, where we will be doing this kind of a scanning. So there are different scanning possibilities are there, one can get information from this. And if we look into the configuration or diffractometer configuration geometry, so something like this arrangement, we have the source and we have the detector and we have the sample will be placed on the position O. So the X-ray will be diffracted from your sample and going into the detector. And if we draw a circle around this, considering this as a radius, and if you draw the circle, and this circle is what we call focusing circle. So in a focusing circle, all three components will be lying. That is source, sample, detector will be lying. And what is Bragg's angle? We know that it's the angle between X-ray source and the plane which is incident to that. And considering this, taking this as a radius, source and detector will be connected, and this is what we call diffractometer circle, or you call this goniometer circle. So goniometer circle is the one which is centered, where the specimen will be at the center, and the at the circumference you can see the source and detector. So now from this we get a geometry. We call this kind of a geometry. We call this Bragg-Brantano parafocusing geometry. In most experimental studies, we will be using this kind of a Bragg-Brantano parafocusing geometry. So in this case, if you are having say different lattice spacing or different interplanar spacing D1, D2, D3, so you can see that their location maybe the red circle and the blue circle and the green circle, you can see that. So the spots you will be getting at different position, which is G1, G2, G3, and all these spots are located on this goniometer circle. So it is devised, the device is made in such a configuration, that is Bragg-Brantano configuration is made in such a way where whatever you are de-spacing, it is going to get connected with the goniometer circle. So here the condition is the R1 should be equal to R2, meaning source to the sample and sample to the detector must be kept constant. So to make this constant, we make certain arrangement in the X-ray arrangement. We go for certain kind of arrangement. Of course, I'll be talking about this shortly. And there are certain cases. In most cases, in Bragg-Brantano configuration, we are moving in this way. Detector will be moving 2 theta to the sample surface. So we'll be moving like this way, where this detector is moving in this way, 2 theta, and incident beam is moving theta towards the sample surface. So this is the configuration we move it. So theta, 2 theta configuration is what we are going to use. So meaning this configuration we will be fixing it. But there are some cases where we will be using a parallel beam optics, especially if you are going to study the thin films. So for a thin film, if you are going to use a X-ray source at a high angle, the penetration will be larger. So if your X-ray is penetrating to a larger depth, then the film information you will not be able to get it. So what we need to control is, we need to control the source must be going at an angle, low angle, maybe 1 degree, 2 degree, 3 degree, or less than 5 degree. So if you are passing this X-ray beam below 5 degree, so the X-ray beam will not penetrate larger into your sample. So thereby you can get information about the surface where film may be there or any kind of surface treatment you must have done. So accordingly, we make this configuration. Of course, we use various kind of collimators. Collimators is going to control this beam divergence. It is going to control different types of collimator, different kind of divergence slits. We will be using it. So this divergence slits are going to control the beam size actually. So yeah, I'll be showing you. So here you can see that the red color ray as well as the blue color ray, you can see that. So what is the beam size which is falling on the sample? You are able to see the sample, the red beam which is falling on this sample, and the blue color beam which is falling on the sample. So if you change this angle, obviously the sample which is or the exposed to the X-ray beam is going to be different. So we need to have a certain control so that we get the information from same volume of the material. So that's where your divergence slits will be helping you to control this. So if you are using a divergence slit, that is going to match the diffraction geometry and the sample size. So at any angle of the beam, it will not exceed the sample size or go very down of the sample size. And we also use receiving side also, we are going to use the slit, and this slit is going to, we are able to see the slits. When it is passed through the slits, it's going to improve the resolution or resolving power. So we can also use variable slits. By using a variable slits, that is according to the angle, the slits will get changed. You can fix the slit size or you can vary the slit size. If you are fixing the slit size, the beam which is exposed on the sample will be different. And if you are varying the slit size, when you vary different angle, the beam length will be kept constant. So the beam, X-ray beam, which is falling on your specimen will kept constant. So here is what you can have a visualize about how X-ray beams are falling on your specimen. So if you are using a divergence slits of 0.05 or 0.17 or 0.25, 0.38, so you can see how the beam size is getting affected by using different kind of divergence slits. So according to your requirement, the divergence slits must be fixed so that you get better information. So doesn't mean that you keep always low divergence slits or high divergence slits. It depends on how best images or best kind of diffraction pattern you are going to get it. And here is the correction about the beam length and diffraction angle if it is exposed to different, if we are using different divergence slits. Of course, we use a solar slit also. Solar slit also control the divergence so that the peak shape will be proper. Sometimes your peak shape will not be uniform; it is non-uniform. So to make a uniform, we need to use the slits, which are the optics. And of course, sometime overexposure of X-ray on your detector is going to affect your detector. So we need to absorb. So sometimes we use attenuator. Attenuator will increase your resolution. So various types of attenuators are being used. We can also use a point source as a geometry. So the point microcapillaries will be used, and these microcapillary will be helping you to focus on a specific part of a component. So here is the microcapillary. So you can use it to control its diameter about 50 micron. So the information is from 50 micron region so that you can have your analysis accordingly. Of course, there are various kind of point source geometry and its design is there. So accordingly, it will be controlled. Even capillary tubes are being used, and in situ possibilities are there, texture analysis and residual stress analysis also there. So you can use various kind of configuration for getting a best resolved the information you can get it. And of course, I'll talk about this on subsequent lectures. So next part is detector is very important. So it's two things are very important: X-ray source and the detector. Either you can increase the X-ray source, that is power of X-ray source, high power X-ray you can use. If you are using high power X-rays, obviously you are going to get a better resolved image, better resolution you will be getting. Your peak height will be larger, so you will be getting a clear information. But sometime it is going to damage your sample as well as some components also it's going to damage. So another thing is it's going to overheat the anode. So thereby continuously you have to take a precautions to cool this anode material continuously. So additional devices, cooling devices you need to provide so that the continuous cooling will be taking place. But in recent technology, what people are doing is they are reducing the X-ray power and increasing the power of the detector. So by reducing the power of X-ray source, you can increase the resolving power of the detector. Even minor amount of X-ray diffracted can be detected by these kind of a detector. So in the market, we have various kind of detector. We can have detectors, something like proportional detector, scintillation detector, solid state detector and all. And I guess most cases in recent equipment, people are using this solid state detector. And now we are getting 2D detector and all in the market, where a point detector is something like a silicon chip where silicon, single crystal silicon will be continuously collecting different points, information like a point, and it is will be counting as a total counts. Whereas, which is called silly detector also. And recent years, we are using a 2D detector or CCD detector. In 2D, two-dimensional detector or one-dimensional detector, where line of silicon chips will be there, and all this instead of one silicon chip, one silicon crystal, you can have a 160 kind of silicon single crystals will be there. All these single crystals will be collecting information at a time, so thereby the resolving power will be increased and the collection information collecting time will be reduced and the sensitivity will be increased. So we can have 2D detector also. Here is an, now you can see the pattern also, and you can correct it and rotate the sample and do whatever you want. If you are not getting a proper information, you can see the pattern how it is diffracted, and you can change the axis or the alignment of your sample so that you can have a better information from your diffraction pattern. So we have different techniques. We have powder diffraction techniques, and we have single crystal diffraction techniques, and we have back reflection Lave method, and grazing incidence diffraction method, X-ray reflectivity, and small angle X-ray diffraction method. So most cases we will be using a powder sample. As name mentioned, you can use a powders as a source actually. So by using a powders, you can get the information and you can go for analysis. And it's better always make it into very fine size. I'll be talking about sample preparation also, where if you make very fine size, you'll be getting better information. So it is about how many planes are rightly oriented for X-rays. So if more crystallites are oriented rightly towards the X-ray source or towards the X-ray, then the diffraction will be, the signal will be more. And if few crystals are oriented rightly, that is, you know, the Bragg's condition. So it's not that all the crystals are oriented rightly to the Bragg's condition, only few crystals are oriented rightly towards the Bragg's condition. So when you are making the specimen, if you ensure that more crystallites are oriented rightly towards the X-ray source, then you are going to get a better signal. So X-ray, powder diffraction, you can use a powder sample, and powder sample, what kind of information you will be getting, what is the phase which is present, and you can go for quantitative analysis, what is the quantity of phase 1, phase 2, phase 3 and all. You can get the information about the crystal structure, you can get the information about the crystallite size, you can get the information about the strain, micro strain which is there. Especially when you are doping something in your material, it's going to increase the strain in the material. Lattice strain will increase. So if at all, if properly doped, it means strain has to change. So crystallite strain is going to give you information about how best it is going to get doped in your material. And also you can get information about the texture, residual stress and all. And grazing incidence is another important technique where grazing GIXD, we call this GIXD. So GIXD is not there in all places. There are very few places you can get the GIXD. So where we are, the incident beam will be focused below 5 degree. So the point is you are going to get information from the top surface. So here is an illustration how we are going to do that actually. So you can see that the angle you can see vary this. So if you expose this to high angle, the penetration, depth of penetration is very important. So by making smaller and smaller, it's of course the diagram is reversed actually. Please excuse me for that. Of course, if you reduce this angle, the depth of penetration will go down actually. So we need to control the penetration depth. So where it can penetrate only few nanometers. So if you are analyzing some kind of a coating or thin films, then you can have it. So either you can control this diffracted from same orientation or that is same plane, or you can make it in different planes also. So accordingly, grazing incidence will be different. So from this, what information we are going to get about the orientation of the thin film? Because often we are looking for whether substrate and the film is oriented in the epitaxial manner. Systematically it is oriented, or it is going to have a different orientation. Is there any kind of lattice mismatch between the substrate material and the film material? And is there any kind of a epitaxial or texture is there in the film? And what is the micro strain or macro strain which is there in your specimen? And of course some kind of a 3D mapping of the polarized figure also you can get out of this diffraction method. And it's possible that you can, when X-ray beam is entering into the sample, it will bend. So you can make the angle in such a way it will be passing through the surface. So this is what we call critical edge. So it's something like refraction from the surface. So you can get information about the surface in this case. So especially orientation events and all, you can study by this kind of a analysis, you can do that. And in case of a GIXT, grazing incidence angle, so as we said, you can scan it at different angles. Omega, you can keep it at 4 degree, 1 degree, 0.5 degree and all. So accordingly, sometimes the film information is very weak. We are not getting a proper signal. So in this case, by grazing incidence, by reducing this angle, you can see the signal intensity is increased. And of course, by keeping it smaller and smaller angle, you will be getting a better signal. And it's also possible that we can use the X-ray reflectivity mode. So sometime the information will be, it's from the reflected sample, it is going to get reflected from the sample. So in this case, that is incident beam is directly monitored. So in this case, if you want to measure the thickness of coating thickness, or if you are having multiple layers of coating, or if you want to find out the density of films actually, and if you want to find out the roughness of the films or interfaces, then you can use X-ray reflectivity method. So again, we have a back Lave method, single crystal method, and we have a small angle X-ray scattering method where this also, especially if you want to, here also the angle will be kept below 5 degree. And the information what you can get is like mesoscale order defects you can get it, especially micropores or mesopores or self-assembled crystallites or molecules are there. Those information you can get it from small angle X-ray scattering, especially those who are working with micropores, mesopores, and proteins, etc. They will be using this kind of arrangements. So of course we can use a single crystal method also, but here again, sometimes we need to cut the single crystal in a specific direction. So for I need to cut the crystal on 111 plane. So you can rotate and get the diffraction from 111 plane and cut it accordingly. Mark it and cut it. So if you want to cut the crystal on a specific direction, yes, you can do that. So later I'll be talking about the sample preparation as well as how to analyze the data. So this part maybe I can talk on Saturday. The slot is given to me. So we will be discussing on that time. So once again, thank you to the organizers as well as all the participants. If you have some questions, I'll be happy to answer you. Any question from the audience? Am I audible? Dr. Ram, if you are there, please coordinate. Yeah, the host is there. Please, can you please coordinate?
Hello, sir.
Yes, sir. Please, sir. Please.
Oh, yes, sir. Thank you, sir.
For iron doped cadmium sulfide, what will be the result? Which I'll be talking in the next analysis part. There we can discuss in detail. Especially when you are doping it, lattice spacing will get disturbed, that is changed. So accordingly, strain will be there. So this part we will be discussing on the next lecture. Preferred orientation in experimentation, sometime you are going to get, usually you get multiple peaks. They are getting from different planes. If your sample is preferredly oriented, then you are going to get a, from one plane you are going to get a very dominant peak. Other planes will be weak. So this also I'll be showing in the next sample preparation. I'll be talking. So there I'll be showing.
அவர் போகணும்ல டாக் முடிஞ்சது ஆன்லைன்ல வா 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 ஆ ஓகே
So here is the information about the preferred orientation. Someone is talking about preferred orientation. What is the effect of preferred orientation? So the conventional X-ray is the blue one, no preferred orientation, but you are getting a signal in the red one. So totally the intensities are changed. And here is another information about the preferred orientation. If you have rotated the sample, original scan is something like this. When you turn the sample, you are getting more peaks. So this is because of preferred orientation. So many peaks, it will appear and sometime it will get disappear, and this is due to your preferred orientation. Of course, some cases specifically we are going to orient the sample in a specific direction to provide maybe magnetic properties or electrical properties. That is different. So you can grow the crystal in a specific way. So that you can do that. Yeah, I'll be talking about the X-ray software. With the software, I'll be explaining how to. So someone has asked about parameters calculation through XRD. So I'll be talking about it, how to calculate all these parameters.
Audience, any other questions? Okay, sir. Thank you very much for your wonderful
Thank you,
session.
doctor. Thank you, doctor. I take this opportunity to give my New Year wishes also. I didn't
Yeah,
start
thank
with
you.
the
Thank
New
you,
Year
sir.
wishes to all the organizers as well as the participant. Happy New Year to you.
Yeah,
Thank you
thank
for
you. Same to you.
joining with us. Thank you.
Thank you, sir. Put anything. Okay. Okay. So இது direct zooms. நீங்க parallel இங்க explain பண்ணுங்க உட்கார வச்சு பாருங்க. சரி சார் பிபிடிஎல் சார் நான் டைரக்டா தான் எக்ஸ்பிளைன் பண்ண போறேன். சாஃப்ட்வேர் தான் நான் இது பண்ண போறேன் ஆக்சுவலா. என்ன Good afternoon, everybody. Myself, Ravikuma from Lab India. So now I am going to explain about our product FTR. Okay. So our brand name Thermoscientific and model Summit X. This is the instrument, and these two are accessories. Okay, and we required one 230 power supply. It will convert to DC power supply. So we require one power supply and one communication cable with software access. So we have a separate laptop with software, and it's a licensed version, and it's a 21 CFR compliance, which will support for pharmaceutical also. So we have our software name Omnic. Okay. So this is the instrument, and this instrument has to maintain in proper humidity and temperature also. So, and I think everybody knows about the basics of FTR. And whenever you are using FTR, that room temperature and humidity should be proper. And same way, you should not allow lots of people around that instrument also. Okay, so that also it will impact in your results. Okay, so first thing. So we have a two module. This is a transmission module, and this is a ATR module. So we can remove and fix this module like this. So remove. Okay. So then regarding this ATR module, we used to call this as a NV and this is a crystal plate. This crystal plate has three types. One is zinc selenide, germanium, and diamond. Okay, so these three depends upon your nature of sample. You have to select this one. Suppose your sample is like only a powder or it's a light density material, then you can go with ZNSC or else germanium. If suppose your sample is like plastics, somewhat hard materials, then you have to go with diamond crystal. So this is the crystal. This is called as Envil actually. This is the crystal. Center part is there, no? That is a where that's a part where we are keeping our sample. So diamond crystal. So in this instrument also you can check your sample in powder powder form, liquid form, whatever sample you can keep directly and keep you can get your spectra. Okay, but in this transmission module you have to prepare your sample in a pellet form. If it is a liquid, then there is a separate cell is there, liquid cell. So you can use your liquid cell and you have to fill that liquid and you can check for spectra. But if it is as powders, you have to make it as a pellet. After making pellet, you have to keep here and then you have to run the spectra. Then for spectra, okay. So this is a transmission module and this is a ATR module. But in ATR module, you can directly keep your sample here and you can after completion you can take back that also if required. If not, you can wipe it out. So and this instrument spectral range is from 350 to 8000 centimeter inverse. Okay, so and with resolution of 0.5. And in this instrument there is a source, MIR source, interferometer, and detector. Okay, very simple. From source you will be getting IR radiation. Through interferometer it will come, and this is a sample compartment. Generally this is a sample compartment. This is a accessible, like you can change your accessories, like either transmission or ATR, like that you can change. This is a sample compartment. In sample compartment you are going to keep your sample. From source your IR source will come through interferometer, and in sample compartment it will observe or transmit, then it will come to detector. Very simple only. So source, interferometer, sample compartment, detector. Okay, so that remaining specification, if you want, I will give you that details actually, complete details, so you can check with that what the detector and everything you can check once also. So whenever I am switching on this instrument, then it will go for initialization, and instrument always do itself its performance. If everything is okay only, then it will indicate ready. If ready indication by instrument, then we can go ahead with further analysis of sample. Okay, so for this instrument, standard is polystyrene film, like how you are checking your HPLC or UV, whatever instruments, no? Like standard is there to calibrate. For this instrument, we are using polystyrene as a standard. Wherever, either in pharma or non-pharma, entirely we are using polystyrene as a standard for this instrument. Okay, so your standard polystyrene have with certificate. So we have to keep our polystyrene film over here, and we have to run. If this instrument result and that standard result is okay, then instrument is okay. Likewise, only we are calibrating this instrument. Okay. So then any doubt? So any other doubts, sir? No. It's very simple only. It's like you are keeping your sample over here and you are starting with software. and it will run the test, and it will give output as a spectrum. That spectrum, either you will go with library search. This FTIR is to identify what the sample actually. That's it. So whatever spectrum you are getting, that spectrum we are comparing with our library, and we are taking what the result, one thing, and another one we are checking with peaks, how many peaks are coming and how much that intensity or absorbance. Okay, so based on that we are interpreting. Actually, that's it. So very simple only. And this software also, Omnic also very user friendly. So you are going to edit your sample name, and do you are going to do background. During background, you should not keep any sample over here. It will go with air media. Then after completion of sample, sorry, background, you will keep your sample. Then you will start the test, and you will get spectrum. That's it. Around 4 to 5 steps only. Okay. So
Any other doubts? Any other doubts?
oh,
Yes.
sample weights. No, so not sample weight actually. Sample weight means you will when you are going for transmission module, that time you will take 1 mg sample, and you will mix it with KBR. Then that case you need to go with weight. But here nothing, whatever sample, but this area has to cover. Advantages of this ATR is no need. I think you know about this transmission technique. So for making this transmission sample, you need to go with hydraulic press. You have to prepare your sample as a pellet form, then you have to keep over here and you have to check. That's a condition. But in ATR, no need to prepare any sample. So whatever sample you have in your hand, you can keep directly. And if it is a powder or like plastic or any other hard sample, you can gently tight this one. Why? Because whatever sample you are keep over here, it should not have any air gap. If it is having air gap, then your result will affect. So for powders, if it is powder, it is better to use fine powders rather than granules. It is better to use fine powders. So then you keep your sample here, and you can gently do tightening of this anvil and start your test. You'll be getting spectrum. If it is a liquid, then you can directly keep your liquid over here, and you can start the test. So after completion of your run, you can wipe it out. Okay. So wipe it out in case if your sample is you have only 5 mg of sample like that, you want to reuse it, then you can take it back. But in this case, in transmission module, it is not possible. So once you prepared your sample with KBR, then that's it. It's like a small tablet like structure, pellets. So once you prepared, that's it. It's a waste. Okay. So as I told you, you can change this crystal. This ATR module is a base module, and you can change with this crystal. This crystal, this is a diamond, and we have another two more like germanium and zettanasi. So okay, that having different spectral range and different applications also. So when you are going for hard material, you have to use diamond, and when you are going for light materials, then you can go with zettanasi also. Okay. So
after getting the fine instrument groups,
which one, sir?
thin film,
Uh,
it is used to ATR system, collected very fine structure.
yes, sir. That's why, sir, whatever sample you are keeping here, it should not have any air gaps. As much as possible, it should be closed with this window, this center part. That's it. Then you will be getting your result. So this instrument is connected with software. That software is Omni. Okay. Then this software having audit trail also 21 CFR, 21 CFR also, like in pharmaceutical they will expect 21 complete 21 CFR, and for like in 21 CFR, like e-signature, data backup, audit trail, everything is there. And we will do on sample analysis with software. If 10 members, we can continue. Interpretation. Like in software, I will explain. Yes. So now it's connected to Nicolette Summitex. So first thing, for very first step, you have to give your measurement name actually, sample name.
Sample name. Yeah.
So just you give sample, whatever it's editable only.
Okay.
I'm giving 7, 20, 25. Okay, then in final format in the sense, what do you want as a result?
Yes.
Like either absorbance, transmittance, reflectance, whatever actually. So you click absorbance. Then number of scans.
Yeah.
Scans, how many times it should do scanning. Okay, so I'm generally we will give 16. Okay, so 16 times it will go for scanning actually. So after that sampling accessory, now I have connected with the ATR, diamond ATR. So it's showing diamond ATR. If I connected with the transmission, then it will show transmission. So here it will show list of this one, Jet germanium. This is germanium, Jet diamond. Okay, and if I want to use transmission, then I have to click transmission. I have to edit that one. Okay, so then resolution 4 remaining same. So I have to give measurement name. Then I have to go with the preview and measure sample. So initially it will go for background actually.
Background.
So start background correct measurement. So first without any sample, we have to go with background. Actually. So I kept 16 scans, no? That 16 scans it is running. Okay, now background correction is completed. So I got the result. Then I am keeping my sample actually. So sample should be flat and it should be, I'm taking as a sample, that's it. So just gentle tight. Okay.
Light type.
Light tight. So then I have to give start sample measurement. So for sample also again it will go with the 16 time scans. So after getting your sample, this is your sample spectrum. Okay. So after getting your sample spectrum, there are three things. One is like you can go with search option. So search in the sense there are pre libraries loaded in this software. We have some like 20,000 libraries are there, like polymers library, alcohols, alkenes, like everything have different libraries actually. If I search it, then it will search with that library, and it will give a result like this: polypropylene, okay, concentrate reinforcing fiber, polypropylene film. So it is matching this whatever sample I run, I got spectra. That spectra is comparing with my library and giving result like this. So it is matching with 99% with polypropylene. This is one condition. So I can take maximum comparison. So another one, uh, I can do peak picks. I can like find peaks. So I can click find peaks. So I can select my range. So like how much range I want to take that peaks. So I can get all the peaks. So then I can save. So based on the peaks, you can interrupt actually. Then suppose comparison also there. Like I have two samples like this. I want to compare these two sample is okay or not. Ready-made, I have two samples. Yeah, because I don't have this any library and all, so I have two samples or 10 samples. I have to compare that sample. So then I can go with Q check. If I click Q check, then previous run also same thing I done. No? So I can click here. Okay. So then it will match and say it will 100%. Same thing previously also I done. Now also I'm doing. So it's 100% it's matching. If it is different, then it will show not matching, like 70%, 50% like that. That's it. So based on that, your wave number, you can go with the further interruption, actually, interpretation like alcohol, aldehydes, whatever, what compound it is, you can handle. Okay. Definitely. Hello. Hello. is in ready condition, green indication. That means only we can. That means only we can use this instrument. Okay, so our software Omnic. So double click that one. So here it will shows green tick mark, and it is connected with instrument. So now it's connected with instrument. So then it's in dashboard. It will shows new measurement. So you have to give your measurement name. Sample 8. Okay. It's editable only. You can give whatever your sample name, you can give it. And final format you want in absorbance or transmittance, like that. So suppose I want in transmittance, I can select here transmittance. If I want in absorbance, I can select that as absorbance actually. Okay. Then I can give number of sample scans. 16. Generally up to 32 we can give. We can give here 16. Okay. Then sampling accessories, I'm using diamond ATR. Suppose I'm using transmission means here we can select transmission or germanium or jet NSC, zinc selenide, whatever you can select it. And then resolution, this and all, keep it as it is. Only you have to give measurement name and final format, absorbance or transmittance. If not also, we can, if you are doing with absorbance, then I want to convert to transmittance means that also possible after completion of your run also. Okay. So do that one and give preview and measure sample. So whenever you are doing with sample analysis, no, like first time you have to go with the background run actually. After completion of background run, you have to use your sample for run actually. Now it is going with background measurement. Start background measurement. So I given there 16 scans, right? That 16 scans are running now. Okay, now background has completed. Background in the sense it will nullify previous noises, everything actually, CO2 noises, whatever previous data, it will nullify and it will make it 0. So now I'm starting with sample. So I'm keeping my sample here. That this anvil should be tightened gently, not so much. Then you give start sample measurement. This is your spectra for this sample. So you can do search option. Like we have a certain libraries, it will compare with the library and it will give a matching results. So this is my spectra. So I have to give search. So I'll get this one. Polypropylene. Okay. This under 99.25, 99.07. It is matching with that spectra. Actually, we have a list of spectra. This is our libraries. Alcohols, aldehydes, dyes, indicators, esters, hydrocarbons. Like so many, around 20,000 libraries are there. Nothing like for polypropylene or polystyrene, we have some standard. We will run that standard and we will save as a library. So same way it will work here. Okay, same way it will compare with the library and it will give a result. One thing. Second, you have to go with peak identifying. How many peaks are there? Go to identify, find peaks, and set the range. See, these are all peaks actually. So based on the peaks, you can further process your spectra. And suppose this is in absorbance mode. See absorbance mode and wave number here. And if you go with transmittance, then you can select this one also. Just inverse. If you want to get the result as a transmission, then it will change here. Use transmittance wave number. Again, you can change like that. It's a vice versa. Then and peak search and quick compare also there. Like I have a two product like this, same product. I want to compare that product. Both are same or not identical actually. So I can go with Q check. So whatever I ran previously now, I can select that one. I give OK. If it is not matching, then it will show less than 21%. If it is matching, it will show 100%. Both samples are same like that. That's it. It's very basic one. Remaining in the audit trailer, data backup, and further interpretation only. So that's it.
Compare returns to observations to transmittance. How to check it?
So if it is in transmittance, so observance now,
Okay.
just click this transmittance. That's it.
இங்கே ஆப்ஷன் இங்கே இருக்கಲ್ಲ அப்சர்வ்
This one, observance and transmittance.
Dear participants, you can ask your any queries regarding FTIR or anything related to today discussion. Shishkumar sir, please unmute them. Let them ask openly.
Price. check.
Dear all, now topic on NMR for biological applications by Krishna Mohan Poluri. Okay, please wait for 5 minutes. Okay, we are going to start this session. After this session, we have demo on BET analyzer and pictometer. హలో సార్ సార్ హలో నమస్కారం సార్ సార్ ప్లీజ్ సార్ మీరు జాయిన్ అవుతారు సార్ ఓకే సార్ థ్యాంక్స్ హలో Ah, profile profile. சார் இங்க வச்சு நீங்க ஸ்டார்ட் பண்ணிட்டேன் சார் லெக்சர். நீங்க ஹோஸ்ட் பண்ணிட்டீங்களா? எனக்கு கேட்கல இதெல்லாம். ஹலோ ஹலோ சார் கிருஷ்ணமோகன் சார், மை வாய்ஸ் ஆடிபிள்? சார் கேக்குதா சார் வாய்ஸ்? சார் நான் போஸ்ட் பண்ணிட்டீங்களா நீங்க? என்ன சார் நான் ஸ்டார்ட் பண்ணதான் வரணும் சார்.
நீங்க ஸ்டார்ட் பண்ணாருங்களா? வீடியோ எப்படி எடுத்த?
போஸ்ட்
ஒரு லேப்டாப் தான் பண்ணுறீங்க.
கிருஷ்ணமோகன். மை வாய்ஸ் கேக்குது சார்? ஹலோ சார் கிருஷ்ணமோகன் சார், மை வாய்ஸ் ஆடிபிள் சார்? சார் கேக்குதா? ஆடிபிள் இது என்ன வரல? Okay. Participants, now is a talk on NMR and for biological applications related to biotechnology and biology medical field by Dr. Krishnamohan Poluri. Krishnamohan Poluri is from IIT Roorkee, Uttarakhand. He is a specialist in structural and computational biology, multidimensional nuclear magnetic resonance spectroscopy, and algal biotechnology, bioremediation, biofuels, biomedical and environmental nanotechnologies. Okay, he is a well distinguished scientist from IIT Roorkee, and also he is the member of Nuclear Magnetic Resonance Society. Okay, with this small introduction, I would like to invite Krishnamohan Poluri sir to give lecture on the NMR and its application in biotechnology and biomedical sciences. Thank you, sir. Krishnamohan sir, please please go through, sir. Please share your screen, sir. Hello, sir. I make you co-host. Please share your screen, sir. Thank you, sir. It's visible, sir.
Okay. Can you hear me? Hello? Can you hear me? Hello? Can you hear me? Okay.
Yes, sir.
So, yeah, good afternoon to all. So, thank you, Dr. Channakeshwar and Dr. Ramanji for inviting me to give this presentation. Today, they told us to talk about a little bit about the spectroscopic techniques and so on and so forth. So, since the workshop is majorly divided into three areas, one is spectroscopy, one is the microscopy, and other one is the material characterization techniques, and so on and so forth. Hence, I decided to give a brief overview of some of these structural techniques, which we use for especially the biomolecules structure and characterization. So there are so many techniques which we use, which is not possible to cover in 1 hour or something. This itself is a lecture course at IIT for almost for a 42 lectures to 50 lecture. So I will briefly tell you what these techniques are and give you a little glimpse of what you can do with these techniques and how you can use these techniques. So for that, what I thought is I will use maybe around a half dozen techniques, that 5 to 6 techniques that I can introduce to you, so that it will be useful for you when you want to analyze. Then you will at least know what these techniques are. So we call these techniques as bioanalytical techniques or biophysical techniques as such. Okay, so if we talk about these biomolecules, so essentially we talk about 4 different biomolecules. So one are carbohydrates. So we will learn a little bit of introduction about all these biomolecules so that when we are going through these characterization techniques, we should know a little bit of knowledge about these biomolecules. So we characterize them into 4 different groups, or classify into 4 different groups. The first ones are the nucleic acids. So where we have DNA, RNA, and all those stuff. Then the other one are proteins. So then we have the other 2 groups, which are carbohydrates and lipids. Okay, so all these things we can characterize. So if you take DNA, RNA, and so on and so forth, so we all know. So the DNA and RNA is made up of 4 different bases. In the case of DNA, it is cytosine, guanine, adenine, thymine. Whereas instead of thymine, you have a uracil in the case of RNA. Suppose if I ask you a simple question, how do I know if a nucleic acid is given to us? How do I know it is a DNA or a RNA? Or if a nucleic acid is given to me, how do I know whether it is a single-stranded DNA or a double-stranded DNA? So similarly, we can thought of the major functions of the cell. These functions comes from something called the proteins. Proteins we have used as enzymes. They are present in ions as ion channels, antibodies, so on and so forth in the nucleus. In terms of DNA replication, that means when DNA is actually making its strands or transcription, DNA is converting into the RNA, or a translation where the mRNA is converted into protein. So we have a lot of proteins. We have almost 20 to 30,000 proteins which are working randomly and continuously in order to make these functions. So these proteins essentially are made up of, the way we have the nucleic acid with 4 nucleic bases, we have something called amino acids. So we have 20 amino acids where we have hydrophobic amino acids, we have aromatic amino acids. In the aromatic amino acids, we have a simple aromatic ring, or we do have something called the heterocyclic rings. We have something imidazole rings, we have indole rings, and so on and so forth. Then we have polar uncharged amino acids, where we have at the end, you have a amido group like CONH2, or simply a hydroxy group or sulfahydryl groups. And you have polar charged amino acids, where these are the ones which are essential to denote the pKa of these side chains, or pi isoelectric point of the protein, where you have acidic amino acids such as glutamic acid, aspartic acid, and you have these ones which are positive, which are histidine, lysine, arginine, where you have the amino groups which are present. So these amino acids. If two amino acids condense to form a dipeptide bond, so you will have two amino acids where with the loss of water molecule, then it will form a peptide bond where you have two amino acids. Okay. Now these amino acids essentially form something called the secondary structures. This is what the basic biochemistry we have studied. They form helices or they form beta sheets. Now in the biochemistry, we have studied about they form helices, they form beta sheets, or they form tertiary structures. That means they can form a monomeric structure, a dimeric structure, a tetrameric structure, a hexameric structure, or an octameric structure. So these are all different tertiary structures. Quaternary structures, the monomer is the tertiary structure. Any oligomer we consider as quaternary structure for a given protein. So now the biggest question what we ask is, how do we say something is alpha helical or beta sheet? What experimental technique you use to say something is alpha helix or beta sheet or something? So that is very important to know what is alpha helix, how it forms. So in theoretically, we have a well-known spectroscopist, structural biologist known as Ramachandra. This is called Ramachandran map. So if the amino acid, these are called phi site. In the basic chemistry, we call them as dihedral angles. If the dihedral angles are in this region, then they are in the form of alpha helices. Here you have the beta sheets. So, but we need to know this map is only useful when you have the dihedral angles. But you need again some technique to measure these dihedral angles. So that means if you take any of these biomolecules, that means whether DNA, whether four bases, whether you want to tell whether it is a double-stranded DNA, single-stranded DNA, or it is a RNA, or you say whether it is a alpha helix, beta sheet, or a dimer, tetramer, or something. What we are looking is you need some techniques which will be. Apart from it, the proteins can have different shapes and sizes. You can see there are uh, helical structures. These are called helical coil structure, or they have beta stranded structures, helix beta strand structures. So knot structures. There are so many of those. Like you can see this as a beta saddle structure. So all these structures you are seeing, I have represented these structures, but now the question is, how do you actually calculate these structures? Okay, so that is what we have to learn. Apart from these, we have polysaccharides, which we use every day. And these polysaccharides, again, becomes very important when you talk in terms of biomaterials. You make a lot of nanofibers, nanomaterials, hydrogels for wounds and everything, using so many of these uh, polypeptide, these common polysaccharides. You can think of chitin, chitosin, cellulose, hyaluronic acid, kerrasinins. These are again seaweed polymers, sodium alginate. So like that, we have so many of these. So and even if you take our human body, we have something called the sulfated polysaccharides, which are heparin sulfate, chondroitin sulfate, dermatan sulfate, etc. So now the question is how are we going to have these structures and how do we do it? So now that is what we need to understand. If I take suppose protein as an example, how do I get the structure of this protein? And if I take the protein can be from a completely unfolded state to a folded state, or it can form fibrils, which is the cause for your amyloid diseases and so on and so forth. So apart from this, these proteins can bind to glycans, they can bind to DNA, they can bind to other proteins. So we can call it them as complexes: protein-protein complex, protein DNA complex, protein glycan complex, and so on, so forth. And now these biomolecules, whether DNA, RNA, protein, or something, they have something called the dynamics, right? So they are not rigid molecules, they are very flexible molecules. So now if you see this spot and in this area, you see all these are cluttered. Cluttered means these are more dynamics as compared to here. So these regions are called more cluttered compared to this one. So that means different portions of these proteins will be, or other biomolecules will be differently dynamic in nature. So we need to measure these dynamics and so on, so forth. Similarly, as a chemist, when there is a reaction happening, when there is a binding happening, what will you look for? You look for some of the parameters called thermodynamics, kinetics, cooperativity, allostery, so on, so forth. So these are all the concepts like rate constant, so on and so forth. These are all the terms which we learned in our chemistry and biology from our +1, +2, and during BSc, MSc, or initial stages of PhD. Now the question is, well, these concepts are present in the textbooks, very good. But now the question is, how do I measure it? People say, okay, hydrogen bond is about 2.5 Armstrong units, very good. But how did you measure that hydrogen bond is 2.5 Armstrong unit? If there is a reaction between A to B, people say, okay, the dissociation constant is maybe 100 nanomole or 100 picomole. Now the question is, how do you know, or how did you calculate the association or dissociation constant, or even for a word, whether the rate constant? How do we measure this? So we measure all these by using something called like bioanalytical or biophysical techniques. We have so many of those techniques. They have very different principles. So I just, we may not explain you all the techniques, but if you see, like the one of the classical or the oldest techniques are the chromatography techniques, where people use ion exchange techniques. So ion exchange will tell you essentially what is the charge which is present on the biomolecule or something. If it has a positive charge, it binds to a negatively charged resin. If it is a negative charge, it binds to the positive charge. Then affinity chromatography. So what affinity it has? Suppose if it is a maltose binding protein, it has the affinity for maltose. So you can use the ligand based screening under affinity chromatography, and the other is size exclusion or gel filtration. Size exclusion means you can actually distinguish or differentiate the molecules based on their size. Similarly, we have something called calorimetric techniques. We all know calorimetry means measurement of heat. So you can measure the heat in this. You can have two very popular or two different experiments. One is isothermal calorimetry, isothermal ITC, actually isothermal titration calorimetry. That means you can add one molecule to the other and you can see whether the reaction is exothermic or endothermic in nature. So you can measure the stoichiometry and all the different parameters such as KD, enthalpy, entropy, and so on and so forth. So similarly, you have something called differential scanning calorimetry. In this differential scanning calorimetry, what you do is you continuously change the temperature. Here, there is a word isothermal. Isothermal means you do at constant temperature. Whereas in the differential scanning, you continuously scan the temperature, and what you see is how a molecule is melting. Suppose if I take a DNA and I do a DSA experiment, I started at 20 degrees and I heat it up to 90 degrees or 95 degrees. Then what happens? The DNA melts and it forms a single-stranded DNA. So then I can see what is the melting temperature of DNA. So if I take two DNA molecules, if they have similar melting point, they are similarly stable. If their melting points are different, that means one DNA is different from that of the other DNA in terms of stability. Similarly, you can measure the mass or size. The two major techniques which you use for mass and size are like the mass spectroscopy, and under the mass spectroscopy also, essentially people use two different things. Of course, mass spectroscopy, you can use it as in basis of gas, you call it GCMS, gas chromatography, GC based MS, or liquid chromatography based thing. That means the compounds which you can essentially, volatile compounds, these volatile compounds, you can come into the gaseous phase and you can use a GCMS, or in the liquid, if you want to do, it is a LCMS. And in this, the two popular techniques are, one, you can ionize the samples using a laser, or you can ionize the samples using an electron spray. So, but all these comes under mass spectroscopy or mass spectrometry. And what all these things tells is, it will talk about the size of the fragment, size of the molecules, to know what are the uh, size of any of these molecules. Of course, you can do, there are some things which you know apart from the size. You can measure the hydrodynamic radius and you can know the shape of the molecules. These are called scattering techniques. So morning also in one of the in the opening registration presentation, so we have something talked about the scattering, CV Raman and the scattering of techniques. So some of them like DLS, dynamic light scattering, which has been used extensively by nano research also. Similarly, small angle X-ray scattering, where people use to know what is the shape of the molecule. It doesn't give atomic details, but it gives. The reason I put all these slides is more or less this 5-day workshop is based on all these essentially microscopic, spectroscopic, and several other techniques. Then we have microscopic techniques where we have confocal microscopy, which is fluorescence based. Then you have scanning electron microscopy, where you see the backscattering of the electrons, and transmission electron microscopy, where you see the transmitted electrons. And we use something else called cryo-electron microscopy. So where you can get, again, atomic resolution structures. Okay, so I will come back to this atomic resolution structure again. And spectroscopic techniques, we have a spectroscopic techniques. I will tell you, we all know the electromagnetic spectrum, starting from, the gamma rays, then X-rays, UVs, then you have infrared, you have microwaves and radio waves. So with all these things, you can do, with X-rays something, you can do something called X-ray crystallography. Then you have an absorption spectroscopy in the UV visible region. Along with it, you have something called circular dichroism and fluorescence spectroscopy. So we will look some of these in the next coming slides. And then you have a IR spectroscopy, which talks about the functional molecules and everything. Then you have a EPR spectroscopy and NMR spectroscopy. Okay. Among all these techniques, remember 3 techniques, which is cryo-electron microscopy, NMR spectroscopy, and X-ray crystallography. These are the 3 techniques which essentially will provide information at atomic level. What do I mean by atomic level? This is called, I mean by atomic level. So whenever you see such structures in any textbooks or in any research papers or something, these structures, the experimental coordinates of these structures are essentially derived by one of these 3 techniques. Either it is X-ray crystallography, NMR spectroscopy, or cryo-electron microscopy. So those are all these techniques. So now what I will do is, for the next 30-40 minutes or something, I will show you what are the applications of some of these spectroscopic techniques. So what I will do is, we will take UV vis, circular dichroism, fluorescence spectroscopy, IR spectroscopy, these 4, a little bit of then X-ray, NMR, and cryo-EM. That means these 4, UV, circular, fluorescence, when I have a protein. Now this protein or a DNA, one, you can have a globule molecule. That means what happens to this protein? That means it may have secondary structures, it doesn't have secondary structures, or it is a single-stranded DNA, double-stranded DNA or something. This is one part which we can tell. This is easy to tell. Second thing is, what are the atomic level contacts that are present in this? That is the second. That is called the fine level details. And these fine level details we will get by atomic techniques. So in the first part, what we will do is, we will see these global techniques. And in the second part, we will see the atomic level techniques. So of course, as I told you, we use the different waves in order to get this one. And if you do this, essentially, when we are talking about these, all the 3 spectroscopy, I will tell you what is the difference between these 3 spectroscopy: UV visible spectroscopy, circular dichroism, and fluorescence spectroscopy. So if you take this UV visible spectroscopy, what you are seeing is how the electron is absorbed. That means how it is going to a ground state, to the excited state. Now, In the circular dichroism spectroscopy, what you will see is instead of a normal light, you are going to put a polarized light. So when you put a polarized light, now the molecule cannot absorb everything, right? So the molecule, we know a chiral center is required for a polarized light. Then the light will be bent towards left or right. This is what we learned in the chemistry in the organic molecules. The third one is fluorescence spectroscopy. Now in the absorption spectroscopy, you have a ground state electron. Now you send it to the excited state. Now the thing is how the electron is coming from the excited state to the ground state. So if it comes in the form of emission light, then that is called a fluorescence phenomenon. So all these, that means if you take UV, circular dichroism and fluorescence spectroscopy, all the three techniques are essentially in the UV visible region, and all the three are essentially dealing with the electronic transitions. But since the nature of the experimentation is different, you will get different information among this. So now this is a simple absorption spectroscopy. Why do people use absorption spectroscopy for biomolecules? The reason why people use absorption spectroscopy is you are essentially measuring one of these transitions during absorption spectroscopy. It may be N to pi star transition, or N to sigma star, pi to pi star transition, or sigma to sigma star transition. Depending upon the energy, the easiest is your N to pi star transition, which you will see in the 400 to 700 nanometers. That means if a compound is going to be colored or something, that means you have the N to pi star transition. And the worst being to be sigma to sigma star, which is in the far ultraviolet region. So it is 150 nanometers. So what one can do is, with this one, I will tell this one, is essentially the UV visible spectroscopy or absorption spectroscopy is commonly used to measure the concentrations of the proteins or nucleic acids. So you don't need to do anything. If you have a protein or a nucleic acid, what you will do is, if you have a protein, simply you measure how many number of tryptophans present in a protein, how many tyrosines present in a protein, and then how many disulfide bonds present in a protein. So you can actually calculate something called the molar extinction coefficient, epsilon. If you know molar extinction coefficient, then you can measure the concentration of the molecule C by measuring the absorbance. You measure the absorbance, you know the molar extinction coefficient, and you know the L, which is essentially the path length, C equal to A by epsilon L, and you measure the concentration. So traditionally, both biomolecules, all the DNA, RNA, and everything are essentially measured the concentration by using the absorption spectroscopy. And it is very easy, in fact, to build a UV visible spectrometer also. There is nothing much in the UV visible spectroscopy. Of course, you have a light source and you have a monochromator where you can know which wavelength you are measuring, and you have a sample holder where you put your sample, and you have a detector where these transmitted electrons are going. This is all what your UV visible spectrometer is. So the light source, heating. So the way you measure is, this is the light source. I have 100 photons coming here, 100 photons coming here, and there are 70 photons which is transmitting. So that means 100 minus 70, the observed number of photons is 30. So that is what your absorbance and transmittance. That is why this is one of the easiest equipment that one can make. But still a powerful thing, since depending upon the absorbed photons, you can tell what is the concentration of the sample. Since, as I showed you, A equal to epsilon Cl, your absorbance is directly proportional to the concentration and the path length of it. So that is why if your concentration is increasing, absorbance is increasing. So you will measure the concentration of these biomolecules or any small molecules. So you can measure the concentration of methyl blue, orange red, any of these organic molecules. And other thing what you can see is essentially you can measure the DNA melting using the absorption spectroscopy. This is one common, very powerful experiments where people do. If you have a double-stranded protein, sorry, if you have a double-stranded DNA, you have less absorbance at 260 compared to your single-stranded DNA. The moment the DNA is essentially melted from a double-stranded to a single-stranded DNA, its intensity increases. Okay, so there is a something called hyperchromic shift. So the hyperchromic shift is due to actually the base stacking opens and the hydrogen bonding is lost. So the electron transitions are different. As a result, you will have this melting transition. So that means you can measure the double-stranded and a single-stranded. These two are different states. So that means what I can measure? I can measure a melting experiment of double-stranded to single-stranded DNA of a particular DNA. This is one DNA D1 and this is one DNA D2. So if I measured this DNA, I got a TM of 77 degrees. I measured this DNA, I got a TM of 83 degrees. If I want to choose the stronger DNA, then I say D2 is actually more stronger than D1 DNA. So you can measure, that means although it's a simple experiment, you can tell the melting points and the stability of your DNA molecules and so on and so forth by using the absorption spectroscopy. The next extension is the circular dichroism spectroscopy. Again, the circular dichroism spectroscopy, as I told, it is the absorption spectroscopy. But what you do is essentially, instead of a simple light source, you use a polarized light. So as a result, this is what happens in the chemistry, that you have a right or left polarized light. Then, of course, if this is a chiral center, then you will see the bend of this light. If not, if it's a racemic mixer, you don't see. So how you calculate the difference? The difference between the epsilon L and epsilon R, that means the left and right polarized light, is essentially the epsilon. That is what you measured. And the instrument setup is, if you see, as simple as your absorption spectroscopy, you have a lamp, monochromator, detector, sample compartment, right? All the four are present. You have a light, monochromator, sample compartment, and signal. What is extra is your polarizer. Whatever the light is coming here is now not a random light. You will put a polarizer so that it will be polarized. So then this polarized light will fall on it. So only optically active molecules will show a signal, and optically non-active molecules doesn't show any signal. So with this, the major advantage is you can measure the secondary structures of proteins, nucleic acids, and so on and so forth. And you can essentially measure the conformational changes of any of these molecules. I will show you some examples. You can see the conformational changes of nucleic acids, proteins, and so on and so forth. So this is how it looks. Now you can differentiate in a protein. This is called helix. This is called a beta sheet. So that means you can tell what is a helix, how does a helix look like, how does a beta sheet look like, or how does a turn look like, right? So these are random coils or turns. This is beta sheet. So you can tell how they look like. And now in a protein, you may have only helix or both helices and sheets or any of them. Then you can measure these proteins. These are proteins. This is myoglobin, okay, and this is N-glycoside. So you can measure these proteins, and what you can do is, like in these, what you can do is you can tell how much percentage of helix is present and how much percentage of beta sheets are present. So you can measure the percentage of secondary structure. Similarly, if you take DNA, I showed an example for single-stranded DNA and double-stranded DNA. Not only single-stranded DNA and double-stranded DNA, even in double-stranded DNA, you have three different types of DNA. Okay, one is called aDNA, bDNA, and zDNA. You see, all are double-stranded DNA, but structurally they are different. How do you differentiate them? You can differentiate aDNA BDNA and cDNA. You can have all the aDNA, bZDNA, zDNA. You can differentiate by using the CD spectroscopy. Okay. So in the case of like zDNA, you have a negative at 200 nanometers and 285 nanometers, which is not present in any of them. Suppose the BDNA, there is a strong negative peak at 255 nanometers. And for a aDNA, there is a strong positive peak, which comes around 265 nanometers. So by seeing this, you can differentiate between aDNA, BDNA, and zDNA by using. In fact, the zDNA has been invented by following the signals of your circular dichroism spectroscopy. Similarly, if you have a aDNA, BDNA, aDNA and BDNA are essentially interconvertible forms. You can convert aDNA into BDNA and BDNA into aDNA. So how do you convert? aDNA and BDNA essentially are, by changing the polarity of the solvent, you can change both of them. So if you see, the aDNA is going to convert into BDNA and so forth. So these transitions you can measure. And one more you can measure for the similar to the, not as powerful as your CD, but even IR spectroscopy, where the chemists essentially use for chemical analysis and understanding the functional groups of symmetric and asymmetric stretchings. To understand, they used to talk about the functional groups, right? So they used to call, there is a carbonyl group, there is a hydroxy group, there is a ester group, so on and so forth. So this also can be used for biomolecules, since what we are looking at is so much of stretching, bending of different groups. So what you can see is, you can see the lipids, nucleic acid, proteins, and so on and so forth using your infrared spectroscopy. You have a separate peaks of the phosphoesters around 1200 or something for DNA, RNA, and around 1700 to 1800, you see, 1700 to 1500, you will have amide 1, amide 2 peaks, which are specific to secondary structural elements of your proteins. So you can differentiate using a IR spectrum, you can differentiate a DNA, you can differentiate a glycogen, which is a carbohydrate, and you can differentiate a protein. Of course, you can all, since you can differentiate a carbohydrate and a protein, you can differentiate between a normal protein and a glycoprotein also. And this IR spectrum is very powerful to identify post-translational modifications. Post-translational modification means I have a protein, I have a glycoprotein. So I can differentiate between a protein and glycoprotein. Similarly, I have a protein and I have a phosphorylated protein. So the phosphorylation is different from that of a normal protein, since normal protein doesn't have a phosphorylation signal or a phosphate group, functional group in a normal protein. So I can easily measure. So that means IR spectra is also used to identify the structural characteristics of these molecules. The next one is the fluorescence spectroscopy, which is the third one of the electronic transition. As I told you, I don't explain completely this one, since we have a limited time. This is called the Jablonski diagram. This diagram essentially, if anyone understands this diagram, even generally in a lecture class or for me, this diagram explanation will take at least a couple of classes. If you understand this diagram, you know what essentially is happening theoretically in a system. So now I told you, this is what you call in a absorption, the green line, the electron excited from a ground state to the excited state. Okay. Now, if the electron decides to come back to the ground state in terms of by emitting light from the S1 state to the S0 state, we call this as fluorescence. And this process is called emission. That is why fluorescence is called emission spectroscopy. So one is absorption spectroscopy or excitation spectroscopy. The other one is emission spectroscopy. The absorption spectroscopy talks about the ground state. The emission spectroscopy talks about your excited state, how the electrons are coming back from the excited to the ground state by emitting light. Okay. So now the main difference between in the instrumentation between a fluorimeter and your absorption spectrophotometer is, if you see the absorption spectrometer, you have a light, you have a monochromator, you have a sample, and you have a detector here, right? You have a detector here. So now, instead of that, in the case of your fluorescence, you are putting a detector which is perpendicular, which is 90 degrees to it. You are not keeping straight, which is keeping perpendicular to it. The reason being, if you put straight, along with the emitted light, you will also see the transmitted light. And the transmitted light is much more stronger than the emission light. So this emission light is masked by the transmission light. Okay. That is why you always keep perpendicular, since emission is in all the 360 direction. Emission is not in single direction, right? It is all in the 360 direction. So you can measure at any direction, but transmitted light is always straight through the sample. And the other difference is, instead of one monochromator, you will have two monochromators, since you have to adjust the wavelength of the excitation, and also you have to adjust the wavelength of the emission. So this is the main difference between your fluorescence and the thing. So now you can measure the folded state of a protein, the unfolded state of a protein, and you can see the difference how the protein is folding, unfolding. Suppose if I have a protein wild type, and if I have a disease mutant, something like R194A, that means arginine is converted into alanine. So this is the disease mutant and this is the wild type. I can measure the melting points and I can say my disease mutant is far lower in stability. It is melting at 2.5 molar compared to 3.5 molar of the wild type. So I can see so many conformational changes using something called the fluorescence. So you can measure these things. And one of the most important thing where people have used this experiment, all the chemists, biologists, nanotechnologists, all the people have used, is something is called FRET experiment, which is fluorescence resonance. Okay. The FRET is essentially energy fluorescence resonance energy transfer. Okay. So this FRET experiment is, instead of one fluorophore, you will have two fluorophores. So essentially what happens is, the first fluorophore, when you excite the fluorophore 1, here it absorbs and here it emits. In the case of FRET, it absorbs, it doesn't emit here. It transfers the energy to the second fluorophore and the second fluorophore emits. So that means instead of you seeing a blue or bluish green light, you will see a red light. So this is called a FRET phenomena. So this is essentially a distance-based phenomena. So you can measure the distance by using these two molecules. And this has been extensively used by all the chemists, material science people, and so on and so forth. So whatever the principles right now, which I had told for all these 3 or 4 spectroscopy or the rest of the spectroscopy, I am showing the examples for biomolecules. The reason being, you may study a lot of small molecules being the chemistry division or something. That is why I am showing the biology molecules. But the principles remain same, irrespective of whether it is a biomolecule or whether it is a small molecule. You see, your absorbance is going to be the same, your emission is going to be the same, or your stretching or bending is going to be the same. But how you interpret the results, how you convert, how you try to understand whether it is a biomolecule or small molecule is different. But rest, the principles and theory are going to be the same. So next 10-15 minutes. So what I will try to do is I will show you the atomic level techniques. Now these are all gross level techniques, right? So whether it is a protein or glycoprotein or something, or a phosphoprotein, or whether you have beta sheets, you don't have beta sheets, so on and so forth. But now, how do you get the structural coordinates of this one? As I told you, structural coordinate means you need to get like this. You need to get protein DNA, protein, or a protein, or whether it is an unfolded, partially folded, or a folded state. So you need to get such lot of information using this one. As I told you, there are 3 techniques which will give this information. The first and the oldest and the most prominent one is X-ray diffraction technique, or we call it as X-ray crystallography. The reason why we call this as a crystallography is you need a crystal. Crystal is nothing but a periodic lattice in order to diffract. So if you get a protein crystal, you will get something called diffraction patterns, electron diffraction maps. From these, you can measure the XYZ coordinates and you can get the structures of the 3D proteins. But the main drawback for this one is majority of the times you don't get the crystals. So the second technique is very recent or very powerful, yet to be powerful, which comes under your microscopy techniques, which is called cryo-electron microscopy. Okay, which is called cryo-electron microscopy. Cryo-electron microscopy is nothing but your transmission electron microscopy only. This is a transmission electron microscopy. You see, you have an electron beam which you are passing through the sample and which you are going through detect it. So the way you do it is here you don't need the crystals. You do something called the frozen samples. Okay, so a beam of electrons is fired through frozen solution samples. Okay, now they can be collected and the transmitted images can be collected. So this is the electron gun where you pass through it and you actually measure the images. How do you get the images? You will get the images like this. You know the transmission electron images of 2D images, negative staining and something. You get the images like this. Now what you do is you do something called projection reconstruction technique. So you take a lot of images and you do a projection reconstruction and then you come up with this one. So this is a recent structure of your Zika virus. So one of the family like coronavirus, this is the Zika virus. This is the whole structure of the total virus. It is not a single protein. So cryo-electron microscopy, now you take all these images. These are like 2D. Now you do something called projection reconstruction and you make into a 3-dimensional image. Of course, the coloring is a pseudo coloring. So you get these structures. That means, think of, we are talking from a simple, you might have done the single X-ray, single crystal X-ray for your organic molecules, inorganic molecules, and so on and so forth. You get the structures of this and you calculated by using Gaussian and everything, HOMO, LUMO levels and everything. From such a simple molecule, I am showing you a structure of a virus, total virus, how the structure is. That also with a atomic level details, right? So that is what the power of these techniques, and the most powerful among all these microscopy is like your cryo-electron microscopy, which is a big sister of your transmission electron microscopy. And the last one is NMR spectroscopy. So the NMR spectroscopy is essentially nuclear magnetic resonance spectroscopy. So you are essentially exciting your nuclear spins and resonating with your radio frequencies. So this is how the spectrometer look like. This is called your superconducting magnet. So the superconducting magnet is made of with cryogases. Inside you have a helium, then outside you have liquid nitrogen. And in that, you will have a niobium alloy where the resistance is 0, kept at 4 Kelvin, which is working as a superconducting magnet, right? So from here, you will send radio frequencies to resonate your nucleus of the given sample. So you can have a sample in a solid state powders, or you can put your sample in a liquid state. You can see both of them. And the beauty of this one is, if this is your periodic table, except the ones which are essentially white, you can see all these nucleus which are present in the periodic table by using your NMR spectroscopy. And the good thing is, you don't need crystals, you don't need frozen samples. You can use any solvent of your choice. You can use CDCl3, you can use methanol, you can use water, you can use a PBS buffer, or you can use a acid. And you can do it both in solid form and a liquid form. So that is how it is very powerful and choice of so many people. Suppose if you take a simple ethanol, so the way it is you have CH3, CH2OH. The environment of CH3 is different from that of CH2 and which is different from that of OH. So you will see 3 peaks and the intensity is, this is 3 times, this is 2 times, this is 1 time. Since you have 2 hydrogens here, you have 3 hydrogens here, and you have 1 hydrogen. And of course, if you go to this molecule of a biomolecule, if a protein is folded, unfolded, or partially folded. Folded means what? It has complete structure. When a protein is folded, you will see the peaks of each and every amino acid very nicely distributed across the spectrum. When it is unfolded, it loses its structure so that you don't see them. And it is like everything is in one place. If it is partially folded, the ones which are folded will nicely spread. The ones which are not folded will be gone. So that means you can differentiate all these different conformations, everything nicely using something called the NMR spectrum. And then you can measure all these things, whatever I have shown, dynamics, molecular interactions, and calculation of structures. As I told you, you can see the unfolded structures, you can see the partially folded structures, nature structures, everything using NMR spectroscopy. So what you do is you take these structures and what you do is you measure some of these distances using a popular concept called nuclear over-Hauser effect. You measure this nuclear over-Hauser effect concept, and what you do is you collect all these something called dipolar distances. You see, from every point, I am collecting some distances. So now you put all these distances and you go on putting in the thing. Suppose I need 1000 distances to get my molecule correct orientation. I can put 200 distances. I can calculate a structure. Then I can see which area is good. These red and green areas are good. The blue areas are very bad. Then from 200, I may add another maybe 300 restraints. So total becomes 500 restraints. Then I calculate again, this is better than this. Then I again add another 500 restraints. I can see the beautiful structure coming out of it. So that is how you calculate by measuring all the distances present between the dipoles. You can calculate the distances. Now you have something called several structural softwares automated where you can measure all these very nice structures. And the idea is very simple. If you have very less number of structural restraints, people with small molecules also like they use something called two-dimensional NMR of measuring toxy, nosy, and rosy to get these distance restraints. Smaller the restraints, bad the structure, more the restraints, you will get such a nice structure. And not only once you get this structure, you remember this is what I am showing. This is the Ramachandran map. Then every amino acid, you will put in the Ramachandran map and you see whether you have a alpha helix, beta sheet, what you are having. So, and if something is coming as wrong in the, if something comes as wrong in the Ramachandran map, that means we did wrong. We have to go back and correct it so that they will come in the correct orientations. So not only that one, suppose this is a protein, I added a carbohydrate octosaccharide to it, then I can also measure where exactly it is binding. Suppose you see lysine 22, it is moving, that means it is binding, whereas these glycine and 33, these are not binding. So you can measure where it is binding, where it is not binding, and you can map it on a structure and you can say, you see, this yellow pocket is the binding residue, not the bottom red pocket. You can tell where exactly it is binding also. And of course, you can measure all different dynamics. NMR is not only structure, these techniques are very powerful, especially NMR is very powerful. You see, I can measure a dynamics of picoseconds. right? 10 power minus 12 to different nanoseconds, microseconds, milliseconds, and different hours in order to make sure what sort of motions that these molecules should have. You see, I can measure these motions in terms of a square called the order parameter. If the order parameter is more, the molecule is rigid. If the order parameter is less, the molecule is very flexible. You see, I can put it on a protein. The more thinner the surface is, that means it is not dynamic. The more it is very dynamic in nature. So you can measure, that means you can say all the different structural elements, you can say the structures, and even you can measure all the dynamics by using these structural techniques. I think I will stop here. This is just an introduction of few techniques. Few of these techniques maybe you will be using it for your you may be learning some of them, like especially absorption spectroscopy, maybe some fluorescence spectroscopy, NMR, maybe single crystal analysis for your small molecules or something. But the idea of teaching this lecture is the same principles. When you go from a chemistry to a biochemistry or a biophysical chemistry, if you are strong with your basic principles, the same principles will actually hold good, and you can apply the same principles for very complex biomolecules, and you can still get the structural data, and which is also true when you use these principles for your nanomaterials or something. Since I am also one of an example where I, like you, majority of you, like I did my bachelor's and master's from chemistry and organic chemistry. Then I learned these biomolecules in the PhD, post-PhD structural biology. And also we are working on nanomaterials. So you can see my Google Scholar page, and any of you, if you have any questions at any point of time, so related to any of these things, the working areas or any of those, so please feel free to contact. And with this, I thank you all. Thank you.
Thank you, sir. Thank you so much for informative lecture. Thank you so much, sir. Uh, Participants, you have any queries, please ask. Participants, please, I think. Dear participants, you have any queries, please ask. Okay. Sir, thank you so much, sir. Small, sir, for a nice lecture. Thank you, sir.
Thank you.
Okay, participant, now demo on the picnometer and beta analysis, BET analysis. Okay, please be in line for 5 minutes. Okay, we will connect you. We will back you. We'll get back you.
Production no mane ne ni kantin.
હું બનાવું બોલો હું બનાવું ખીચડી જેવું બનાવું વઘારેલી ખીચડી જેવું જે બનાવવું હોય કઢી સાદી ખીચડી કે વઘારેલી જે બનાવો કઢી ખીચડી સાદી ખીચડી હોય તો કઢી ખીચડી ખાવ કઢી ખીચડી તો કઢી ખીચડી ને જે બનાવો દાલ ખીચડી બનાવો દાલ ખીચડી ગાજર સીતે નહીં દાદા દાલ ખીચડી દાલ ખાઈ લે છું કાલે રોહિત શર્મા કદાચ જ રમે એવું કોણે કહ્યું તમે જાણો પ્રેસ કોન્ફરન્સ હતી તા પેલું શું કહેવાય ભાગલા પડી ગયા છે ટીમમાં રોહિત શર્મા જગ્યાએ બીજો કોક કેપ્ટન બનાવો છે
डॉल्बी विजन IQ, लेकिन उससे फर्क नहीं पड़ता क्योंकि इस टीवी के खुद के अंदर ही एम्बिएंट लाइट डिटेक्शन बोर्ड देखने को मिलता है। सो आपके रूम के अंदर अगर लाइट बहुत ज्यादा है तो